Hello everyone, in this video we're going to be solving a non-standard equation. I call this non-standard because we have an exponential function on the left hand side and on the right hand side we have a rational function. So we're going to be able to solve this problem by using a little bit of guess and check and a couple other things. First of all, let's go ahead and call the left hand side f of x and do a little bit of calculus. If you set f of x equal to 2 to the power 3x squared minus 2x cubed, then you can go ahead and differentiate this. To differentiate a to the power u, where u is a function of x, you just need to write the same thing. And let me go ahead and erase and write it here. So if you're differentiating a to the u, a is a constant, u is a function of x, you're going to write a to the u. And then you're going to multiply this by ln a, and then finally by the derivative of u, which is u prime. So u prime comes from chain rule, and we just need ln a as a correcting factor because our base is not the Euler's number e. We just need to change the base in that case. Anyway, so using that property or rule, we get 2 to the power 3x squared minus 2x cubed times ln 2 times the derivative of the inside or the exponent. In this case, it's 6x minus 6x squared. 6x minus 6x squared. That's going to be the derivative of the inside from chain rule. Makes sense? So this product is the derivative of our function f of x. And as usual, we're going to set it equal to 0. Even though this kind of looks like a complicated product, you only need to focus on the polynomial piece. Because this can't be 0, this is a constant, so the only thing that can be 0 is this one, which is actually very, very easy to solve. So let's go ahead and set 6x minus 6x squared equal to 0. And then by factoring, we get 6x times 1 minus x equals 0. And from here, we get two x values. X equals 0 and x equals 1. And by using these values, we can actually make a table, all right? And our table is going to look like this. We're going to have kind of like 3 rows with top row x, the middle one is f prime, and the bottom one is going to be f. And now we're going to put our roots for the derivative here, 0 and 1. Those are our critical points for f. So at this point, we can go ahead and take a look at the signs, plus and minus signs. Looking at this product, where do you think it's going to be positive and where do you think it's going to be negative? Just test any of the values. Like you can use x equals 2 because these are x values, right, in the top row. If x is 2, obviously, our derivative is going to be negative because of the 1 minus 2. So we have a negative sign here. And obviously, on that certain interval from 1 to infinity, it's always going to be negative. And then it's going to change sign in every root as long as they are not double roots. And then it's going to be minus again. This gives us a lot of good information about our exponential function, which is not an ordinary exponential like this one or like this one or whatever. It has some bumps. Okay. Maybe kind of curves around a little bit, I should say. But here's how it goes. If the first derivative is less than 0, that indicates the function is decreasing. Otherwise, it's increasing, and then it's decreasing again. So we're supposed to have a minimum here and a maximum here. And let's go ahead and take a look at the values. For x equals 0, our function is going to be 2 to the power 0, which is 1. So we're going to have a 0, 1. That's going to be a minimum point. And at 1, we're going to get 2 to the power 1, which is 2. So it's going to be 1, 2 is going to be max. So this gives us a lot of good information about our function because if you think about it, 0, 1 is going to be here. So you're going to have a minimum there. So you have something like this. And then at 1, 2, you're supposed to have a maximum, which means our function is going to proceed like that. So we kind of got the rough idea of what our exponential function is going to look like. Make sense? Okay. So that's our exponential f of x. Now let's go ahead and take a look at a couple other things. Obviously, from this picture, this should be almost obvious that when you take the limits like limit as x approaches negative infinity of 2 to the power 3x squared minus 2x cubed is going to be, as x approaches negative infinity, looks like this is going up, right? Increases without bound, it's going to be positive infinity. You can definitely verify that, because as x approaches infinity or negative infinity, this is going to be more important than x squared, grow faster, and of course there's a minus sign. Negative infinity to the third power with the minus sign is going to approach positive infinity. Okay, and as the limit as x approaches infinity of the same function, this time you might be expecting to get positive or negative infinity, right? But that's not the case, because if x approaches infinity, this is going to approach negative infinity, and 2 to the power negative infinity is going to approach 0. Make sense? So our limit in this case is going to be 0, which means this is supposed to be like a horizontal asymptote. I mean, did I say horizontal? Yeah, I said it right. Anyways, I thought I said it wrong. Now let's go ahead and take a look at the other piece, which is what we're going to call g of x. G of x, and since I have x squared plus 1 all over x, I can write this as x plus 1 over x, because x cannot be 0, so I'm able to separate them. And now this is going to be our g of x. Let's go ahead and do pretty much the same thing. Let's take the derivative and make a table. If you differentiate this, the derivative of x is 1, the derivative of 1 over x, something you should definitely memorize if you're doing calculus, negative 1 over x squared. But you could also write it as, power rule. And now, by setting this equal to 0, we get two simple solutions, x equals negative 1 and x equals 1. And then let's go ahead and make our table. So our table is going to look like this. We have g prime this time and g. We have the negative 1, positive 1. And now, one thing to keep in mind though, x cannot be 0, right? So we have something interesting at 0. It is the vertical asymptote, okay? So you have a vertical asymptote at 0. You got to be careful. That's actually going to split up the function into two pieces. That's why I use that dotted line for that. But let's go ahead and take care of the signs now. Now, if you look at the derivative, when x is greater than 1, something like 2, you're going to get a positive value. Otherwise, you're going to get negatives. But since we have to split it up, I'm going to write that twice and positive again. So our function is kind of like increasing, decreasing, and then the next piece picks up as decreasing, and then it increases. So we kind of have like a max here and a min here. Now, here is what we're going to look like. And x equals 0 is obviously a vertical asymptote. We already talked about it, right? Now, let's go ahead and take a look at some values. What is the g value at negative 1 and positive 1? At negative 1, g is going to be negative 2. At 1, it's going to be positive 2, right? So let's go ahead and write this down. Now, the negative values are not really going to help us, because if you look at the g values, we don't really care about a type of intersection. Oh, here's what I'm going to do, though. Something to talk about. When x is negative, g of x is also going to be negative. Think about it. Negative plus negative, right? So our functions cannot intersect. Our g is going to be in this region. And when x is positive, it's going to be in this region. So there might be some intersection points, right? There might be 2. There might be none. You never know. So what are you going to do? Well, when you look at the minimum value at 1, you notice that g of 1 is equal to 2, right? What's that supposed to mean? We also have f of 1 equals 2. That means we have actually a common tangent. You know what that means? It means that there's going to be a single intersection point. Let's write this down. G of 1 is equal to 2, and f of 1 is equal to 2. So that means they go through the same point. But not only that, g prime at 1 is 0, and f prime at 1 is 0. They both have a horizontal tangent at that point. Make sense? So they have a common horizontal tangent, which means there's going to be a single intersection point, which means x equals 1 is the only solution. Let's go ahead and take a look at the graph. The graph will make much more sense. Okay. Ta-da! This is what the graph looks like. And as you can see, x plus 1 over x is actually two pieces. One of them is making a max, the other one is making a minimum, where the other function, the exponential, is making a maximum. They intersect at a single point, which is at x equals 1. And that's the only solution to this non-standard equation. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.